Hi, everyone. Thank you for coming to this talk. We came to understand that Go offers strong support for concurrent programming. While the Go programming language has lowered the barrier to writing concurrent applications, concurrency remains difficult. Tony Hoare commented in 1985 on multithreading. In its full generality, multithreading is an incredibly complex and error-prone technique, not to be recommended in any but the smallest programs. Well, how many of you adhere to this principle? Because I'm not. Because concurrent programming in Go is fun. It's easy to start a Go routine, allowing our programs to become faster through asynchronous or parallel execution. We have so much fun that we can't stop. We use Go routines and channels. Everything is getting better, faster, more parallel, more efficient, until things don't look quite right anymore. But never mind, this program doesn't listen to us anymore. It's now going full throttle, spinning, and oh, I hope there's a billing limit for the cloud provider we are paying to host this. Well, first and foremost, don't panic. Who said this? What do you think? It's part of the Go proverbs introduced by Rob Pike, and this proverb means don't call the panic function for normal error handling in Go. It goes back to the effective Go document. But it's also a quote from Douglas Adams' A Hitchhiker's Guide Through the Galaxy. In the novel, the words "Don't panic" are printed on the cover of a guidebook with the same name as the book, an electronic encyclopedia and survival manual for travelers throughout the galaxy. The guidebook's cover offers this advice to help people stay calm despite the unknown and often absurd challenges they encounter while hitchhiking through the universe. Writing code sometimes feels like hitchhiking through the universe. The talk doesn't follow a straight line or offer a one-size-fits-it-all solution for writing a concurrent cache. Instead, think of it as a story, a guidebook, an example, and a toolbox for possible approaches as you find yourself building a concurrent data structure in Go. So what is a cache? It is a software component that stores data so that future access to this data can be performed faster. Another definition is remembering the result of an expensive operation to speed up reads. Applying a cache in Go could look like the following. Okay, how come I have an interest in this topic? Since I joined Reddit in 2019, caching has always been a prevalent theme for us. Here's a photo of me in 2019. Here's a photo of my manager at that time. Here's a photo with the both of us. We look very different today. But as you can see, I was always motivated to build and ship caching. And this year, I had an opportunity to build caching at a different scale. I'm part of the ranking platform team, a team that's developing and maintaining ranking services. And ranking services are responsible for fetching, sorting, and filtering content to build feeds for the user. We have our ranking service deployed in Kubernetes, and we pull the data we need to filter posts from another service. We need different things, so let's call this service thing service. To improve our latency and resiliency, we decided to start caching some of the data in a distributed remote cache. In this case, we use a Redis cluster where the data gets cached across different nodes, and each node has its own set of read replicas. We fetch cache data from Redis and perform a write if there's a cache miss. A growing demand on this Redis cluster increased the cost to host this cluster. We're pulling between 5 to 20 million keys per second from this cluster. and most of it is CPU bound. So in order to scale down the cluster, we would have to make fewer requests. I was asking myself, is this cacheable per pod? So a local in-memory cache might not make sense because each pod must fetch cache data redundantly, and we might be talking about, I don't know, maybe 90,000 operations per second. But I was curious to give it a shot. So we can define a cache type as a struct with a map for fast lookups. In this example, both keys and values are strings. And you might want to yell, make it generic. But I like to start with the use case I'm writing it for and then generalize later if needed. We need to decide how we want to expose this internal map. Set and get method for a single key would be very common. And we want this cache to be thread safe, meaning accessing it from different Go routines should be safe. We can use Go's sync package. A typical choice here is to use sync.Mutex. Mutex stands for mutual exclusion and is a lock primitive. In both operations, we need to acquire a lock, writing to the cache, as well as reading from the cache. Or better, we could use a sync.RW mutex, which stands for reader-writer mutex, allowing multiple reader Go routines, but one writer Go routine to access the cache. This is an excellent API for a general purpose cache that, you know, maybe you could like start publishing as a third-party library at some point. But we don't want to build a general purpose cache. We want to design one tailored specific to our problem. And in my case, we always need to look up multiple keys, often up to 2,000 per call. We can use this constraint to influence our API decision and instead expect multiple keys for get and various items for set. I like the simplicity of this code. Integrating the cache and deploying it to production would have probably brought us back to this screen. Because only adding entries to the cache but never deleting them means we will see unbound memory growth. What we're lacking is an eviction policy, also known as cache replacement policy. Cache replacement policies answer the question, when new data should be cached, which data should be removed to create room for the new data? Laszlo Bilaldi already thought of the optimal replacement algorithm, which would remove the entry whose subsequent use will occur farthest in the future. An algorithm that cannot be implemented because it requires knowledge of the future. We can create an algorithm that will approximate what we think will happen. And there are different cache replacement algorithms and a whole taxonomy of policies. Common ones are LRU and LFU. LRU stands for least recently used, which favors entries that are used recently. LFU stands for least frequently used, which favors entries that are used frequently. Both of them sound useful to our problem because on Reddit there will be popular posts receiving more frequent traffic, but also as time goes by, posts become less relevant. Recency should also play a role. Let's illustrate how a cache policy like LFU already increases the complexity of our cache. We want to keep track of how often an item has been fetched, and this information needs to be stored per item, so we need an additional type to wrap our value. We add a frequency field, also called reference count, and we use a min heap that will provide us with a fast way to retrieve the smallest items in case of an eviction. We add the item to the map and push it on to the heap. And as we add more items, we can see them being pushed into the binary tree data structure of our heap. And so fetching entries means their importance, their frequency has to change. As we retrieve the item, we have to update their position in the heap with the frequency that will be incremented by 1. And because reading data now also requires us to modify the data structure, we cannot make use of the reader-writer mutex anymore. If we fetch entry A and B, we will see entry A move down, entry B switch sides, and entry C move to the top, so that the entry with the lowest frequency, C, will be quick to retrieve for potential removal. Adding a fourth entry D to the cache, it gets inserted close to the top. And so assuming our cache has a maximum size of 3, this event would trigger an eviction. Entry C gets removed and deleted from the map as well. Okay, this was LFU cache eviction 101. And you might be thinking, what about all these other types of eviction policies? I want to see examples for all of them. Yes, there are many more, and I recommend checking them out, but let's go back to our original problem. Designing a local in-memory cache as a second layer in front of Redis, and to decide whether I should start with LRU or LFU or something else, I wanted the ability to measure different performances. And if gophers hear performance, all they can think of are benchmarks. Benchmarks help us to measure the performance, not limited to execution speed, but any metric we're interested in and that we can observe. Benchmarks also enable us to create a baseline. A baseline helps us to determine how much better or worse an alteration of our code is and whether we should release it. Go provides excellent support for writing benchmarks out of the box. Functions with the prefix benchmark are considered benchmarks. And similar to test functions, they get passed in a unique type called B, which is used to manage benchmark timing and specify the number of iterations to run. On our end, we should make sure to provide a stable environment, which means don't have programs running that occupy the CPU, don't execute benchmarks on shared hardware, don't browse the web while you're waiting for your results. I know that one is really hard. I mean, what are you supposed to go? Just walk away from your computer? Okay, let's write a benchmark for the get method of our cache. We define our benchmark function and set up the benchmark loop. And everything we need to prepare for the benchmark, we put before the loop, like instantiating the cache, filling it with entries. And then just before we start the loop, we call reset timer to ensure that the elapsed time has been set back to 0. Finally, inside the loop, we call the method we want to benchmark. Easy, right? So, and then we can start a benchmark just like that. And because I assume there will be variance, I specify the benchmark to be, let's say, run 5 times. This is what we get. It tells us about the operating system, the computer architecture for which package it ran the benchmark, and the type of CPU that was used. Then for each benchmark run, the number of iterations that were run and how long one iteration on average took, specified in nanoseconds. You can absolutely benchmark like this, but for my specific case, I started to run into limitations. For one, we have to write a benchmark for each individual operation, a benchmark for set, a benchmark for the eviction portion. For another, this one doesn't test all code paths. Like the way I set up the cache here, we're only testing the scenario where we get a cache hit for every key and no cache miss. For cache hit rate, what ratio should I even pick? 10% cache misses, 20? How would I go about generating the data? I wasn't very happy. I felt like I was, again, moving further and further away from my actual problem. The benchmark also doesn't include any Go routines nor concurrency. I want to measure how set and get behave as different Go routines call them. For this, I decided to generate a sampling of real data from production. So I created an event log of cache access over a time span of 30 minutes, including timestamp of access and post keys requested, which allowed me to exactly replay what would happen without having to analyze the statistical distribution. To address the lack of concurrency, Go's benchmark library provides a solution. brun parallel runs a benchmark in parallel. It creates multiple Go routines and distributes bn iterations among them, depending on what Go max prox is set to. In a benchmark, it would look like this. The function body paths to run parallel will be executed in as many Go routines as Go maxprox defines, and each one will run as long as pb.next reports true. And so because they run in Go routines, we have to set up any state local to the Go routine inside the function body. And so with this in hand, my benchmark quickly evolved to something like this. There's a benchmark case utility type I defined that stores any relevant information about the benchmark. Inside run parallel, we collect per Go routine benchmark results. And inside the loop, it will fetch the next event log. Then it will go and attempt to look up the keys, and if there's a miss, update the cache, which allows to somewhat simulate what would happen in production code as well. Normally, the issue now is that we only get back one measurement, measuring the entire loop reported as nanoseconds per operation. But thanks to b.report metric, we can take our own measurements and report custom metrics. This was great, because now I felt confident that I could actually start comparing different implementations, different cache policies for the first time. And so here I was comparing LRU and LFU eviction policy. And we let each benchmark run 10 times, because each benchmark run might stop at different times in the event log, which could influence the hit rate. I decided to pin the number of iterations with the bench time flag, meaning each benchmark will process exactly 5,000 event log entries. And this is what I got. So this is a lot of data, but if you can pick it out, we can see already the difference between LFU and LRU in terms of hit rate. But there's a better tool to aggregate this. Another tool you will find useful in those scenarios is called bench stat. And so instead of only printing out the results, we could write it to a file and then call bench stat, defining a custom column so that it will compare the results from the same benchmark invocation. And this way we get a much more readable result. In terms of hit rate, LRU performs a lot better. Reads and writes are over 40% faster. And the speed difference makes sense to me because LRU is typically implemented with a doubly linked list, which can operate faster than a heap. I wasn't quite ready yet to drop the idea around frequency, because I felt like there should be something to be gained from not only looking at recently requested posts. Taking a look back at our taxonomy of cache replacement policies, we can see there's a couple of hybrid policies. For example, ARC, Adaptive Replacement Cache, which keeps track of both frequently and recently used entries, plus a recent eviction history for both. ARC isn't unproblematic though, because IBM has a patent on it since 2006. Then there's LRFU, which stands for least recently, frequently used, and is a classic policy that combines both LRU and LFU. LRFU goes back to a paper from 2001, where similarly to LFU, we manage our cache with entries and order them by account. But instead of incrementing each entry just with one every time, the increment is calculated based on how much time has passed and a weight parameter. The weight itself determines if the policy should act more like LFU or more like LRU, with values ranging from 0 to 1, each representing the extreme of either policy. Or we pick a weight somewhat close to the extremes, and we get LFU with just a pinch of the LRU policy. I did run into issues implementing this because we need to calculate the recency frequency score, CRF, for every entry, every time we need to compare them. This in turn requires raising the number to the power of a potentially large number, which for one isn't very cheap, and for another can be prone to floating point overflow. Also, new items start always with a score of 1 and are likely to be quickly evicted again. Maybe this was also the problem with the initial LFU implementation. Then I came across DLFU, decaying least frequently used. This is an approach I found on the website of the author of a Python reference implementation, Donovan Barter, a Google SRE from Australia, who has analyzed the initial paper and seamlessly figured out that the approach can be simplified by recognizing that A, the LRFU decay is a simple exponential decay. B, the exponential decay can be approximated using the cache size, which would in turn eliminate having to use math.pow. And C, we can exponentially grow the reference increment instead of exponentially decaying all entries, thus requiring fewer fields per entry and fewer comparisons. I found this implementation much more approachable, and I can only thank Donovan. We had a lot of correspondence on the topic, and his insights were incredibly valuable. In fact, I'm only showing an excerpt on some of his ideas, and if you find any of this interesting, please check out the links and consider reaching out. So let's take this and convert our LFU cache to a DLFU cache, because both can be implemented with a heap. We set up the decay based on the size and weight. And then starting with the set method, let's rename the type and move the eviction portion into its own method. Oh, and surprise, we're also incorporating item expiry now. And we made the value of the cache generic. So instead of recency, we call this reference counter score and add in check for item expiration. And we can apply this for get as well. And so when we retrieve the item, we now also want to check if it's already expired. And instead of incrementing the score by 1, we increment it by the current increment value, the decay that happens at the end of the fetch. So the increment is the value which will grow over time in order to decay older entries out of the cache. Okay, this feels like a substantial change, and in the previous benchmark, LRU got ahead, and this one combines both. So I was able to compare LRU against DLFU implementation. Now, I was pretty pleased. We get a much better result in terms of hit ratio. However, read and writes are slower. And having those benchmarks set up is great for another reason. Not just getting those results, but generating a pprof profile by simply supplying the dash CPU profile option. So this way we can run the benchmark, use gotool pprof to open the results. And we can list top nodes, but it might include other portions only relevant to the benchmark. So I often prefer to work with the list command, which lets you display the code and time measurements in line. The left column shows us the flat time, the time measured in the sampling for one execution. And in the right column, it shows us the cumulative time, the total time measured in the sampling, executing this line over and over again. Heap updates are expensive over time. This is a known trade-off compared to LRU. But I thought locking would take up much more time. But interestingly, acquiring a lock doesn't really take a lot of active CPU time. So instead, to measure how long a go-routine has to wait at a lock, we can use the block profile instead, which we generate with the block profile option. Looking at this output, we can, again, use the list command, and oh, that's a lot. So of like 10 minutes of waiting time that the profiler observed, half of it alone was spent on the lock for get and for set. And yeah, it's a lot of time waiting. In a way, I'm not surprised, because we only have this one lock for both reads and writes. And this portion here is our critical section. It's the part of the code that we want to protect from concurrent access, where we want to have some guarantees around mutual exclusion. So instead of locking the entire method, we can use more fine-grained locking and start like moving the locking and unlocking into the loop itself. And we could probably optimize this even further, because potentially we could use a different lock for increment, but I try to keep it simple. And comparing this against our implementation, we already get a considerable speed up. At the same time, reads are still taking over a millisecond, which is not that great. I think Redis can respond faster. But I thought this good enough to test in production. So I was very excited to get this out. But my enthusiasm was greeted by a spike in the number of coroutines. Memory usage went up and requests started to time out. Roll back. The latency added to the call paths that integrate the local in-memory cache was simply too high. Because I still wanted to make incremental progress, I made use of two techniques. One is to sample how often the local cache would be used. For example, setting it to only perform cache lookups for 1% of requests, or 2, or 10. So this in turn allowed me to slowly increase it until I find the point at which it wouldn't scale anymore. And the second one is to perform cache lookups in goroutines and then make use of context timeouts to abort if it doesn't return time. So for the cache lookup, it would look like this, that instead of like just looking it up, we check our sampling flag, and if it returns false, we return early. And then we can wrap the call to the cache in a goroutine, create a new context with a timeout, and then we wait until the context is done, either due to the cache returning in time or the context timing out. And we can take this even further by also passing this context to the cache. Because when the cache is under a lot of concurrency contention and the goroutines start to time out, then this loop would continue to add pressure to our mutex, while we'll already have decided we won't look at the results. So this may seem excessive, but it did allow me to roll out the cache in production to a limited degree. And not only did it already reduce the number of calls to the remote cache, but it also made it possible to profile it in a production environment. That said, I wasn't done with optimizing this cache further, which brings us to the last topic, moving beyond sync.Mutex. So a word of caution, if you look at the standard library, or any library for that matter, don't assume. Don't do what I did. At least read the documentation. This is a little bit embarrassing, but when it came to SyncMap, I thought it's just an untyped map with a sync.Mutex under the hood, which is wrong. So I highly recommend that however you're writing code, try to set it up in a way that makes it possible for you to jump from using any library to the definition of the code. I always find it incredibly insightful to just see what's actually going on, and I always discover more than I thought. Which, yeah, here in the case of SyncMap, we can already see it's definitely not just an untyped map with a mutex. So I decided to revisit the documentation, and to be fair, it did remind me why I thought it's just a map, because of the first line, but it says like, not is, so. And this map is specialized for two use cases, where the entry for a given key is only ever written once, but read many times. For example, a cache that only grows. And where multiple goroutines read, write, and overwrite entries for disjoint set of keys. So put differently, goroutines have ownership over a specific set of keys. So this actually doesn't apply to my use case, but I included it because I think SyncMap adds further evidence why it makes sense to design your own data structures in Go, because there are just certain use cases that allow for specific optimizations. It did make me curious, though, if there are other versions like that out there, and it brought me across SyncMap, which is a third-party library providing a variety of concurrent data structures for Go. SyncMap is a concurrent hash table that uses a modified version of cache line hash table data structure. The idea of CLHT is to organize the hash table in cache line size buckets to reduce the number of cache line transfers. What? Could you repeat this a little bit slower? That's at least what I thought when I first came across this. So I had to read up on some fundamentals to gain a better understanding. So with modern CPU architectures that are based on symmetric multiprocessing, individual CPU cores are typically connected to a shared memory. And to speed up reads, a CPU core has different levels of also caches called L1, L2, L3. The specifics might differ. But the closer the cache is to the core, the faster it will be, but also the smaller it is going to be in size. And then there's something called locality of reference. And this principle says if a processor accesses a specific memory location, it will likely access the location in the near future as well, temporal locality. And it will likely access also memory nearby, which is spatial locality. To make this efficient, not an individual memory location is copied, but instead a whole cache line, also called cache block. This can create problems. So let's say there's a variable x and y, and in our code they are defined next to each other, and they become part of the same cache line in main memory. A thread on CPU core 1 reads variable x into its cache, and because it's contiguous, variable y is also read into the cache. Core 1 has now exclusive access to it. A thread in CPU core 2 now reads variable y, which causes a downgrade of the line in the first cache, which results in both lines being shared between CPU core 1 and 2. Core 1 writes the variable x, and because the cache line is in a shared state, it must invalidate the cache in core 2. If core 2 writes the variable y, it will get a coherence miss and must invalidate the line in the first cache, which forces core 1 to perform a coherence write back. And then that in turn could repeat into the other direction as well and can create some inefficiencies. Nonetheless, the cache coherence protocol is essentially what takes care of ensuring that each CPU core has a consistent view of the same data. But this added coordination between CPU cores can impact application performance. And so maybe with this knowledge, it's a little bit more clear what SyncMap tries to achieve by making sure that the access of elements that are in the map map as well as possible to individual cache lines. So how can we use SyncMap now to improve our cache implementation? Because of the heap, we still need a mutex to synchronize access. To utilize SyncMap, I decided to move the cache eviction into a Go routine, and instead of constantly maintaining a sorted set of elements, I would just collect all entries and then sort them. Other shared data like numeric or string types can be also made accessible in a thread-safe way by using atomic primitives instead. Based on what I learned, I was almost reluctant to call this lock-free because in the end, the CPU still needs the coordinate access, which is really not that different from locking. So we can set up a continuous for loop that will take care of the trimming, the eviction part of our cache, and as well as offer a graceful shutdown. And so during trim, we collect all items and then sort and delete as many items that are over the threshold. So we can remove the locks, update the map access operation with the ones that SyncMap exposes, and then lastly use atomic primitives for the increment and score operations. Okay, let's see how this performs in our benchmark. Running it against our previous iteration, we get a big jump in performance. The hit rate increased, writes and reads are 100 times faster, but we don't get it for free. Eviction is now almost 2,000 times slower. And so if we look at a profile, we can clearly see that most of the time is spent towards sorting these elements. There are many optimizations to be taken from here, and one actually was suggested in the performance channel of the public Gopher Slack. And because sort uses pattern defeating quicksort, and we don't really need to sort all elements, we could make use of quick select, which is a linear algorithm that can find the kth smallest elements. And yeah, sure enough, it did provide a nice improvement. Of course, eviction is still very slow, and there are further optimizations we could make. For example, deleting items during collection based on a heuristic, figuring out which score will be the right cutoff point to start deleting items as we are iterating the map. But nonetheless, these trade-offs made it possible to fully roll out the cache in production and significantly reduce number of calls that have to be made to Redis. At the same time, these trade-offs work because the amount of data that is added to the cache is low enough that our pretty slow eviction method is still able to keep up with it. Because if we would increase the writes for this, we would struggle much more in terms of memory. Okay, let's summarize. So this example illustrates why implementing your own data structure can provide a lot of upsides. It exposes you to the possibility of optimizing the code based on properties that are possibly unique to your use case. And we covered a range of cache replacement policies, most notably DLFU by Donovan Barda, which is similar to LFU but has an exponential decay on the reference count. We covered how to write benchmarks, but more specifically how to utilize parallel execution in benchmarks to test specifically for concurrency. And also using the Go profiler to look for potential bottlenecks. At the same time, both of these tools work very well together because we can set up a benchmark that covers our case, and we can at the same time use the profiler to dive deep into the performance of what's going on underneath. We also did a quick dive into the cache coherency protocol, and while this topic requires a lot more content, it's good to know that sharing memory across different Go routines will affect performance. And to me, this gave a completely new meaning to the Go proverb, share memory by communicating. As well as just moving to atomic primitives, for example, doesn't mean that there's no locking involved anymore. We have just decided to push the problem further away from us and let the hardware handle it. At the same time, on machines with many CPU cores, it does have the potential to provide performance improvements. Last but not least, please don't generalize from the talk's examples. write your own code, construct your own benchmarks. I guarantee you, you will be surprised. And once you're surprised, you will start asking questions. Thank you.